It's a pleasure to be here speaking to you all, Provost LeBlanc, members of the community, students and faculty at Rosenstiel and the University of Miami. I have to say that it is somewhat of a intimidating matter for me to come here and talk to you about the ocean, because I know that everyone here absolutely lives and breathes the ocean. You spend all of your time thinking about the ocean, playing on the ocean, studying the ocean. And when I heard that the title of this series was Sea Secrets, I thought, what can I tell you that you don't already know about the ocean? So with that in mind, I titled my talk, No Big Secret, because I really doubt that much of what I'm going to tell you today is going to be news to any of you. But I hope in some of the stories and vignettes and little pieces of information that I pass on today, there will be at least one new thing that you'll learn about the ocean that you didn't know ahead of time. So what my general theme is I want to talk about the ocean's impacts from climate change and from climate choices. Because what we're doing right now is we are faced with choices for how we are going to respond to climate change. And some of those choices might be acceptable for us, but the question is, how do they impact the ocean? And because our lives are inextricably linked to the health of the ocean, don't we need to consider how those climate choices impact the ocean in deciding our paths forward? So that's the general theme. So I don't need to tell any of you that the climate is changing. This is just a map that shows observed change in surface temperature. You see massive red, yeah, okay, everything's warm. Some places are even warmer than others. The amount of heating has not been uniform. It was interesting, I was at University of Missouri, I think it was last week, and to introduce my talk, they had a string quartet, so 4 instruments, that played the temperature record from tree rings, from and other pieces of data from 1880 to the present, with the 4 different string instruments, one playing the equator, one playing the subtropics, one playing the mid-latitudes, and the other playing the pole. And they all started together in 1880 and ended up in the present day. And you could hear the various cycles, the El Niños and the decadal oscillations, but of course it was building to the crescendo of today with the pole going eek at the end, and of course the equator not getting quite so bad. But what a beautiful way to use music to illustrate what's basically in this map of how much the globe is heating, and not uniformly, with the poles taking the brunt of it. Okay, so these climate change is not just in temperature, because this cascades to ecosystems, people, and ultimately to our economy. So Science published a special issue in November of last year that talked about the sea changes that are happening because of climate change. And there were a number of excellent articles in that I recommend to you. And here were some of the biggies in there. It talked about rise in sea level, about changing and displaced fisheries, about rising ocean temperatures, about ocean acidification, and about the expanding oxygen minimum zone. All of these are direct ocean impacts that are happening from our release of CO2. Now, this diagram from a very reputable publication, this came from National Geographic, is basically everything that is wrong with what we don't teach properly about sea level rise. This is a map that shows what an Earth without ice would look like. And what they basically did was they melted the Greenland ice sheet, they melted the Antarctic ice, and they just filled up the oceans and they said, okay, this is what would happen if all the ice melted from global warming. And this is wrong, wrong, wrong. This is not what would happen. What you see from this is a lot of the coastal areas inundated, and you see Antarctica flooded. Well, this is wrong on so many levels because what happens when ice melts is so much more complicated. So where do I start? The first thing that happens is, oops, I got these out of order. The first thing that happens is if you take the ice off Greenland, Greenland rebounds just like the Northern Hemisphere rebounded after the glaciers melted. This is called post-glacial rebound. So at a location like Halifax, if you melted all the ice, Halifax actually comes out of the ocean. It doesn't go underwater, it comes out. And other places more distant from the ice sheets actually sink down even further. So places like Florida go down even further. And so they get even more underwater than a map like that would show. So it's not a simple matter to predict what the Earth would look like if all the ice melted. Another issue is that the rise in sea level is only partially predicted by the melting of ice sheets. A big factor of how much sea level rises is by the warming of the ocean itself. Fully half of the sea level rise that we're seeing right now is not from the melting of ice sheets, but from thermal expansion of the ocean itself. When water warms, it expands and rises. And this is just a little animation showing over 6 decades, so starting in the upper right-hand corner there and going to the present day with the blue colors showing a colder upper ocean, and going to the present day with the warmer colors showing the ocean temperature today, how much the temperature has warmed, and all of that warming has resulted in thermal expansion of the ocean, and therefore half of the sea level rise is due to this warming of the ocean. So if you want to predict how much the ocean is going to rise, you also have to know how much heat content has gone into the ocean. Well, it turns out that the amount of warming is measured in 150 zettajoules of heat energy, and that's how much heat has gone into the ocean just in the last 17 years, or last 18 years. And a zettajoule has so many zeros after it, I don't even remember how much a zettajoule is. But to put it in perspective for you, the amount of heat that's gone into the ocean from the greenhouse effect is equivalent to the heat energy from a Hiroshima-sized bomb every second for 75 straight years. So take that much heat every second for 75 years and put all the heat in the ocean, and that's how much heat we put in from climate change. It's a heck of a lot of heat. And all that is now thermally expanded, and it's coming up on your shores. Okay, so there's another component to sea level rise. It's not just the melting of the ice, and it's not just the thermal expansion of the ocean, but there's also a component to sea level rise from circulation of the oceans. So this picture here, this big red thing, is the dynamic height of the ocean surface from circulation of the ocean, how much the ocean is held up above. So imagine the ocean was perfectly still and didn't move at all. There were no currents, no tides, no nothing. So the ocean was perfectly still. It would be a smooth surface. Now we start the ocean moving, and we have the Gulf Stream. Because of the Gulf Stream, there's topography on the ocean, and it's actually higher offshore Florida because of the motion of the Gulf Stream. It's higher in the west, and it's lower over here in the east because of the fact that you've got currents on a rotating sphere. Now, that's kind of a steady state topography as long as the Gulf Stream doesn't change. But if the Gulf Stream gets more vigorous because, say, there's larger temperature gradients because of global warming, then it could raise sea level even more. And that could flood Florida even more. If the Gulf Stream got less, then it could mitigate maybe some of the flooding. Right now, we don't have really good predictions of what's going to happen to the Gulf Stream. But this is something we'd like to know, because dynamic topography on the ocean can make another difference as to how much sea level is going to change. So all three of those factors are very important as to how sea level is going to affect you here in Florida. And it's also not the gradual rise in sea level that causes the problem, because there's short-term variance that's superimposed on it. So if you imagine that you're standing here and gradually you see yourself moving downhill because sea level's rising or you're sinking with respect to the ocean, superimposed on that is all sorts of variability due to storms, hurricanes, El Niños, etc. And so all of that short-term variability is much larger than that slow, what is in your reference frame, a slow rise of sea level as you're sinking beneath. So that even though sea level is rising pretty slowly with respect to you, these short-term variability can make a huge difference. And in fact, that's what many communities in Florida are experiencing right now. Whereas it may be just millimeters that the actual shoreline has changed, but those millimeters can make a huge difference when there's a huge tide, because you superimpose that short-term variability on a long-term trend, and it means that yesterday's 100-year flood is tomorrow's high tide. And then another impact that we're seeing, this is Hurricane Katrina, which was, of course, a devastating impact when it hit New Orleans. But in addition, it became the largest human migration in US history since the Civil War. So it was not just the immediate impact of it. The amount of people that were displaced changed the geography, the human geography of the US in a way that it had not changed since the Civil War. So this is an important thing to remember. And there are other effects, like this was Hunan. that was a hurricane that hit the Philippines. It was in a class of its own. It hit in 2013, and typhoons draw their energy from the heat in surface waters. And in that year, there was this pool of hot water in the Western Pacific, which eventually led to the El Nino that we now have off the western US. But that pool of hot water sat off the Philippines. And typically, typhoon winds stir up deeper, colder water, and that's what sucks eventually the energy out of typhoons and causes them to lose their force. That year, the typhoon hit that pool of hot water and actually grew stronger. It was the strongest typhoon to hit the Philippines in many decades. So these are mostly the sea level rise, the effect on weather. There's also the effect on fisheries. In that same science issue on ocean impacts, there was an article by some fisheries scientists from up in New England that talked about Cape No Cod, and basically how after the fishermen fished to the point where it wasn't a viable fishery in off the Grand Banks, lots of restrictions were put in, and the restrictions on fishing should have allowed the cod to recover, and they never did. And what the fisheries scientists later found out was that there was no place on the planet that experienced more ocean warming than the Grand Banks. The Grand Banks was ground zero for ocean warming, and the temperatures there got so warm that it was no longer viable for the cod. So the cod were never going to recover there. And therefore, there was no hope for the fishery once it got to a critically low level. They could not come back. And then this diagram, also from the same issue of Science. This is a paper by Lisa Levin and her co-author Labrie that just shows some of these other impacts on a cross-section. This is a notional cross-section across the Pacific, showing trenches, and then the eastern Pacific here, showing that not only is there warming, but there's growing ocean acidification and the growth of oxygen minimum zones. Now, acidification is a growing threat to the oceans because of the many ways that it is affecting ocean organisms. First of all, it affects the ability of calcifiers to make shells. And so there are many organisms in the ocean that depend on these calcium carbonate shells. And because the ocean gets more acid, the acid basically dissolves their shells. They can't build them, and it's sort of like, wow, I don't have my skin anymore, and therefore I'm not viable for living, so forget me. So that's one problem. But acidification negatively impacts even animals that don't have calcium carbonate shells. And it works in the following way. So acidification affects the pH of the ocean. And animals in the ocean have developed their biochemical processes that depend on a certain pH. All of us depend on in our blood, in fluids in our body, everything has to be a certain pH. And if it's not a certain pH, we have to buffer our cells to adjust the pH to be right for those biochemical reactions to happen. So when those animals in the ocean find that the ocean is not the right pH, they have to expend extra energy to buffer so that the pH is matched across their cells with the internal and external to the cell, so that they can have those reactions occur appropriately. Now, that extra energy they have to expend to buffer the pH inside and outside their cell wall, that's energy that they could otherwise use to grow, to reproduce, to do anything else, to do life functions, to swim, to feed, other things. So if they're expending that on buffering against pH, at some point, something else has to give. So acidification is threatening life in the ocean. Now, these oxygen minimum zones are another problem because they're growing in the ocean as the temperature changes. These oxygen areas increase. What happens is we have increasing fluxes of this particulate carbon that fluxes down, and it absorbs the oxygen as it decays and creates these growing dead zones in the ocean. And many of you might know that the largest animal migration on the planet is not the wildebeest that we see on National Geographic, but the largest animal migration on the planet is actually a daily migration of animals that go from the deep sea at night, or during the day, where they hide from predators, and they come up to the surface to feed at night in the dark where they can't be seen by those that want to eat them, and then they go back down at night or during the day to hide again from predators. Now, as this oxygen zone that's dead grows, it becomes difficult for them to migrate across it because they can't breathe in it. It's sort of like us going into a room that someone sucked all the oxygen out of it, and you have to get through that room to get to your lunch table. And now, instead of the room being 100 feet wide, so you take a breath and dash through the room to get to the other side where there's your food and more oxygen to breathe. Now the room, instead of being 100 feet wide, is 200 feet wide. And you don't know if you can dash through a room 200 feet wide while holding your breath. That's what they're having to do. So it's a problem. So all of these are impacts to the ocean. What are we going to do about it? Well, we've got a couple choices. We can mitigate for climate change. We can adapt to climate change, but we're not sure we can adapt the ocean to climate change. Or we can do climate change intervention. And I'm going to talk briefly about all three of those. So mitigation is things like solar panels and other ways that we just stop climate change at its source. Climate adaptation. Here's a picture of climate adaptation. There's going to be a lot of this going on in Florida, probably not too long. And climate intervention is things that we could do, like this is an industrial scale plant that is actually sucking CO2 out of the air after it's already been emitted. Okay, so this is like, some of you are probably familiar with CO2 scrubbers in submarines. That's what this is. Instead of being in a submarine, it's just out in the air. Okay, they're expensive. It's better not to emit the CO2 in the first place, but it's possible to do if you want to pay enough money. Or another way of climate intervention is this. It's to put particles in the air that change the Earth's reflectivity to sunlight. And you can quite effectively cool the planet by changing the amount of sunlight that comes in. It's not going to do anything about ocean acidification, but you can cool the planet that way. And I'm going to talk about those methods. So this is a plot from another plot from science that shows 3 possible climate futures. So which of those scenarios we're going to do, mitigation, adaptation, climate intervention, sort of depends where we find ourselves on these curves. We start back here in 1960. Here's when we could have done something at Kyoto, but no, we dropped the ball, we didn't do anything. Here we are today, where we have the Paris Accord. And here we go future to 2040, where the Paris pledges end, and we go into the future. And this is a plot of global emissions of CO2 as a function of time. So how much mitigation, adaptation, and climate intervention we do will depend on which of these curves we choose to follow. This one is business as usual. This is what we've been doing so far up till today, is the business as usual. And this one is the scariest one for the ocean. This is the one that we're on right now with the Paris pledges. This one here is the path to 2 degrees C. When everyone talks about, wouldn't it be nice if we kept the Earth under 2 degrees C of global warming? Well, this is what 2 degrees C looks like. It's pretty drastic, pretty drastic. It requires massive overhauling of our energy system. It requires embracing nuclear energy. There's no path to 2 degrees C that doesn't have nuclear energy in its mix. Okay, so I'm going to set aside this for the moment. The area under this curve, the total emissions, would keep us under 2 degrees C. I'm going to assume, I think almost optimistically, that we're going to be somewhere between this curve and this curve. I'm hoping that we've decided against business as usual, and we'll be somewhere between this two. Now you'll notice that when the Paris pledges run out, there's still an increase in emissions. The reason for that is that even when Paris pledges run out, China pretty much flatlines, United States emissions flatline, European emissions flatline, but other developing nations still go up because they're going to want to have the quality of life we have. They're going to want to have the energy use we have. My personal view is the number one thing we could be doing as a developed nation is help developing nations not install fossil fuel burning energy. If we could help them leapfrog technologies and go immediately to renewable energy and avoid this curve and instead have them flatline like China, that would be the number one thing we could do to help the oceans. Okay, so if we could do that, then this curve could actually, instead of going like that, might actually flatline and be more in this region. And of course, the oceans can be part of our energy solution. There's plenty of energy in the oceans. Wind energy, energy from tides, energy from currents, but that's unfortunately not well enough developed in terms of tidal energy and other kinds of energy in terms of harnessing. So it's going to take major effort to get there. So let me go on to mitigation, because I know that this is something that's a big issue here in Florida. This is a map that the USGS put together that showed the most vulnerable areas for sea level rise. Any area in green is an area that's probably pretty hardened to sea level rise. These are the rocky coasts of the US. Any area in red or yellow is an area that is going to be very vulnerable to sea level rise. You notice that the Gulf Coast and Florida is mostly red and yellow. So it shows that those areas are highly susceptible to damage from sea level rise. So what are the sorts of things that can be done in the way of adaptation to sea level rise? Well, one interesting study that was done, this is in North Carolina off Alligator River, and it shows what an organized retreat from sea level might look like. And this is a simulation that shows what sea level rise is going to look like over the next 150 years or so as sea level rises there. And you can see that this area loses about 1 million acres of land. So what they've done in order to guard against this is the following. They've used oyster reef construction and done a natural tree planting and things that Mother Nature herself does to protect the shoreline. And with this, they hope that the oysters themselves are going to colonize and make a natural reef here that will help this area better weather the sea level rise. Now this turns out to be a wildlife sanctuary, so it's a good place to try this out. Another strategy for high value investments, which might be more like downtown Miami, this is San Francisco, is to do triage for high value investments where you actually have to worry about where you can't really retreat from the sea level. And this is what's happening in San Francisco, where they're concerned about areas around the Mission District. This is the Bay Bridge in the background here, and this is where AT&T Park is, and concerned about this level flooding, this area flooding in here, where there's a lot of new development. Now this is an area that actually can be hardened against sea level rise because of the kind of, it's on mud, but they actually can put seawalls up. I'm not sure whether that's going to work as well in a place like Miami where you're on karst topography. And this is one of the great engineering challenges, I think, for the future, is how to deal with development on karst topography. And this just shows some of the dynamic topography of some of the storm surges that come in that could flood these areas. One last area of adaptation I wanted to mention is restoring natural processes, that shorelines will actually prograde under rising sea if you restore natural processes. We've dammed too many rivers, and that stops sediment from reaching the coastline. And if we allow those rivers to run free again, then we deliver sediment. And this has been one of the big problems in New Orleans, that we've stopped the river from running freely. And so that can help. And this is just an example of a dam that was pulled out. And once it was pulled out, the shoreline started to prograde again. So since I'm running out of time, I wanted to go to my last one, which is climate intervention. And the question that was asked of a committee of the Natural Academy was whether climate intervention, otherwise known as geoengineering, whether that could be a third tool in addition to mitigation and adaptation to combat climate change. What are the prospects for making carbon capture scalable and affordable? What are the risks? And how controllable is albedo modification, which is spraying aerosols in the stratosphere? And we produced 2 reports which are available online at the National Academy's website. So first we looked at carbon dioxide removal from the atmosphere. And that's enhancing, for example, enhancing natural carbon sinks through changes in land use management, accelerated weathering, ocean iron fertilization, or human-made methods, direct air capture and sequestration, and bioenergy with carbon capture and sequestration. So the committee said a definite yes to changes in land use management, a definite yes to direct air capture. Those were mature technologies, and bioenergy with carbon capture and sequestration, a definite yes. Geologic sequestration of carbon dioxide is practical. There's plenty of places to store it underground, but we need to do more studies as to how to contain it and make sure there's no leakage. Now, ocean iron fertilization was the one method of carbon dioxide removal that we did not give a green light to. How many here are familiar with carbon dioxide or with ocean iron fertilization? Okay, not all of you. So ocean iron fertilization was the brainchild of a man named John Martin, who was the director of Moss Landing Marine Labs in California. He uttered one of the most famous one-liners in all of oceanographic history. And he said, "Give me a tanker of iron and I'll give you an ice age." And what his hypothesis was at the time was he noticed that there were areas of the ocean in which there were plenty of nutrients for microscopic plants to grow, but there was not a lot of plant life. So he said, why are there all those nutrients out there, but there aren't plants taking it up? What's the missing ingredient? And he hypothesized that the missing ingredient was iron, that they were iron depleted. The oceans were iron depleted, and that if he put small amounts of iron in the ocean at the ratio of 1 to 1,000, that would be enough to get the oceans to bloom. And the oceans would suck carbon dioxide out of the atmosphere, and he could get such magnificent blooms of plants that would take so much carbon dioxide out of the air that it would cool the planet so much we would go into an ice age. Well, it turns out that John Martin tragically died of a brain tumor before anyone could prove whether his hypothesis that iron was the missing nutrient in the ocean was right or wrong. But it turns out that from space, there are only two things that are man-made that are visible: the Great Wall of China and the lights of night. And when scientists went out to test Martin's hypothesis, they added a third to the list. Oceanographic research ships went out and they trailed a slurry of iron in the ocean, and the bloom was so large that satellites saw it from space. So that led to the thought that you could cool the planet by dumping iron in the ocean. Well, our committee considered this as a possible remedy for global warming and decided, no, it's not ready for prime time. First of all, you can't guarantee what's going to bloom. It could be some toxic algae that's going to poison ocean ecosystems. And secondly, there's no guarantee that the CO2 stays in the ocean. The plants could die and it could be re-emitted to the atmosphere. So we decided more research was needed on this. So we decided that this method was ready for increased research and development, to scale it up to scales that matter, to minimize energy and materials consumption, to identify and quantify risks, for example, in ocean iron fertilization, to lower costs, and develop reliable sequestration and monitoring. And so the question is, will this scale in time and space? And then finally, I want to talk a bit about albedo modification. This reduces the amount of sunlight absorbed by Earth in order to cool the planet's surface. We considered two strategies: atmospheric aerosols and marine cloud brightening. And Albedo modification is just another word for changing the brightness of the planet so that you affect the amount of incoming sunlight that's reflected back to space. And the reason why this is believed to be a viable method is that we know that it happens about once a century. There's a major volcanic eruption that spews sulfur dioxide into the stratosphere. Last time this happened was the eruption of Pinatubo, and it cooled the planet by 1 degree Fahrenheit for a couple years. So we know it works. Volcanoes do it about once every 100 years. So the thought is, gosh, we could send some balloons or airplanes up in the stratosphere, put some particles up there, and do it artificially. Well, there are risks. It affects the ozone, so it makes the ozone hole worse. It changes the amount and patterns of precipitation in ways that we don't fully understand. It has no impact on carbon dioxide levels or ocean acidification, so it doesn't solve the ocean acidification problem. And it has poorly understood regional variability. So it has significant potential for unanticipated, unmanageable, and regrettable consequences. For example, we've had this big drought in California. If someone did this and the drought got worse, you'd probably blame whoever sprayed the aerosols. So we decided, no, don't do this. Should not be deployed. We considered the double moral hazard, however. The double moral hazard is another word for you're damned if you do, you're damned if you don't. That if we even did research into albedo modification, it could be seen as a disincentive to mitigation and adaptation. But if we don't learn more about albedo modification, we could someday have our backs against the wall if we don't mitigate, if we don't adapt, and we have nowhere to go. And someone wants to do albedo modification, and we don't know if it's a good idea or not. If someone wanted to do it tomorrow, we don't have enough information. So we decided we probably really do need to do research. We need to do research because tomorrow, I, as the incoming president of the National Academy of Sciences, could get a call from the White House, and the president could say, someone sprayed aerosols up in the stratosphere to cool the planet, Saudi Arabia or someone else. And we need to know, what's the impact going to be? Should we do something? Should we let them do it again? And I have to say, I don't know, because we don't have enough research to answer the question. So we basically need to know more about this. Or someday the president could call and say, we've got data from NOAA's observing network that we've got massive release of methane along the entire continental margins, and it's coming out at prodigious rates. What should we do? Should we do an albedo modification? And I'd have to say, I don't know if it's worse than this climate emergency you've got or if it's better. So that's why we need more research, and we also need a better observing system so that if we did research, we'd be able to monitor what the results of that research is. And we need governance. And we need more than just scientists involved in decisions on climate intervention. If we do some intervention, we have to have people who care about the oceans at the table, because we have to understand which of these various interventions, what their impact is on the ocean, and people who know that our future is tied to the health of the oceans as well. So the bottom line, we've been stalling climate change mitigation. We've not gotten serious about adaptation. Carbon dioxide removal is likely to remain slow and expensive relative to other choices, absent any policy changes. If you're scared by albedo modification, you should be. It will not address the majority of ocean threats. And if you don't like it, see 1 and 2 above.